Okay, folks, last day, which seems a little bit hard to believe, unless you have class tomorrow, of course, but last day for CE 3063. Quick update on where the student opinion survey is. We broke 50% sometime over the weekend, which is fantastic, so thank you to those who filled that out. If you're watching the lecture as a video now, wondering if I'm giving away answers to the exam, please use this time wisely to go and fill out the student opinion survey using the QR code that's placed on the first slide. There's nothing new today. All I want to do is kind of put some bookends to the course. When I introduce the course, I laid out the entire framework for the things we are going to be discussing throughout the term. And so I'll just remind ourselves of where we started and where we're ending up now that the course is over. And I also want to give a little bit of context for what you might be expecting once the course is over and once your degree is over, and what your future might look like in terms of career prospects or continued education. So this was the course map that we followed the entire term. And so before we started this class, you probably didn't know what steel shapes were. You probably didn't know necessarily where bracing would go in buildings or what the gravity framing was for, how to calculate dead live snow and wind and earthquake loads in accordance with the building code, and you probably never heard about notional lateral loads before. So we placed all that in the context of limit states design, where we want to figure out what we expect the loads might be. We're going to factor them up a little bit, and then the rest of the course is about making sure that the members are strong enough to support those factored loads. So we talked a lot about steel members. From lecture 11 onwards, we talked about tension members. We looked at modes of failure. We looked at welded and bolted connections. And for each of those, we discussed the shear lag effects and how the net effective section is less than the net section when we're calculating the tensile rupture strength of those kinds of members. We talked about compression members, how they might buckle. We talked about columns and buildings. We talked about effective lengths. Then we went to talk about flexural members, where we looked at braced and unbraced bending, talked about shear resistance and deflection. The last couple of days, we started putting these things together. We looked at combined tension and bending, compression and bending, and when we have compression and bending, we looked at the P-delta effects and overall member stability. So we've got a lot more to do, of course, but we can't fit it into this course. And so if you're interested in the stuff that we talked about and want to learn more, next winter you can take CE 5063, which is more or less a continuation of this course. I would say it's a continuation insofar as we're still talking about structural steel. But in that class, we talk more about structural steel systems. And so we focused a lot in this course on tension-only bracing. We looked a little bit at tension compression bracing, but we really just focused on braced frames. In the other course, I talk about moment-resisting frames, something called Gerber framing. If you look up at the roof of a Sobeys or a Superstore, you might wonder why the roof sort of looks the way it does. It looks different than a typical multi-story structure. We talk about those. We talk about the connections in the buildings, and we talk about bridges a little bit. And I also laced in seismic design a lot more into the design of the systems in a lot more detail than we would have been able to have covered in this class. Okay, so just to remind everybody kind of what we've been up to, the first part of the class was calculating loads, and the rest of the course was calculating strengths. And where the loads and strengths meet are the structural analysis, and we spent a lot of time in lab talking about doing this stuff with STAAD Pro with the overall goal of limiting the probability of failure to something that was acceptable, right? So we looked at all these things, and so of course on the exam you're probably going to have to calculate some tensile resistances of things, right? If I give you a bolted connection, you're probably going to have to calculate the block shear resistance and the net section fracture resistance, considering for net area after bolt holes are removed and shear lag effects are accounted for. And if there's a welded connection, there's probably some shear lag effects. If it's a welded HSS, there's some net area effects. And so you can expect to be doing these kinds of calculations on the exam on Saturday. We talked a lot about compression members. The first equation we looked at for compression members was this one, where we're basically going from mechanics of materials AFY to mechanics of materials pi squared E over K over R squared, all wrapped up in this nice little equation. For sure, you're going to have to use this equation to calculate the compressive resistance of something on the exam, right? And so in that case, you're probably going to need to know how to calculate FE, if it's for weak axis, strong axis, torsional buckling. You're probably going to have to verify that we're not going to get local buckling before we get the compressive resistance of our member, making sure that you can use A and not some reduced effective area. And you're already calculating KL over R anyway to throw up into the equation for lambda for the most part. And so when we think about limit states for compression members, we've got ultimate limit states, which includes local buckling, checking to see if you're going to get local buckling. And then you're going to make sure that your KL over R ratio is less than or equal to 200, and you're going to calculate that your compressive resistance is enough for the load present on the column. Then we talked about flexural members. We looked at braced bending. So depending on section class, you're going to calculate phi ZFY or phi SFY. Probably you're going to have to calculate phi ZFY or phi SFY on the exam. Probably going to have to calculate MU on the exam for unbraced bending. Probably going to have to calculate VR, and probably going to have to look at deflection in some way. Okay, so everything on each of these slides is particularly important. At the end, we started putting some stuff together. We reformulated everything in terms of relative utilization. And so we calculate what's called an interaction ratio, which looks at the combination of tension and bending or compression and bending. And I squeezed all this into 3 lectures. It was really quick for all the stuff that we talked about. If I ask you something about combined loading, it's not going to be as rigorous of a problem as what we went through in the last couple of examples. Calculating U1, calculating the interaction ratio for the 3 different limit states. You probably just don't have time to go through all that stuff on the exam. I probably could do that to you, but the amount of time you'll spend doing these kinds of calculations on the exam is relatively limited compared to the other things. Okay, so perhaps some suggestions there, read between the lines as to where you want to focus your study time for the course. So at the start of the course, I introduced these learning objectives, and so now that the course is over, you should be able to identify the key parts of steel structures like braces, columns, and beams. That's the most basic level, and I'm sure everybody can do that. Should be able to differentiate between which members are going to be tension members, compression members, flexural members, or members under combined loading. Pretty easy for the most part. Braces tend to be tension or compression, columns tend to be compression, joists and girders tend to be flexural members. Members under combined loading, a bit more tricky. You have to do some structural analysis and look, does my member have tension and a bending moment? And if it does, then it's a member under combined loading. But we didn't get into that too much in this class in terms of identifying what those members might be, though I did give you some hints as to where you might find those kinds of members. Ultimately, some of the goals here are to design steel components using S16 to resist the loads prescribed in the National Building Code of Canada. Dead live snow, wind, and earthquakes generate effects on the structures. We can calculate the strengths, and importantly, you should be able to navigate the CISE handbook mostly to do this stuff, right? So in the handbook, you've got design aids. There are column selection tables, which are just basically compression member selection tables. I don't know why they call them columns, but they do. There are beam selection tables. There are bolt selection tables. There are properties in the handbook and the orange pages to help you calculate areas that are required for tension. Lots of stuff in the handbook that you're going to have to be able to use for the exam on Saturday. Okay. Now you should also be able to model and analyze some steel components in STAAD.Pro structural analysis software. If you hated STAAD.Pro, don't take CE 5063 because you're going to start modeling buildings in 3 dimensions, looking at earthquake load effects in 3 dimensions. If you love STAAD.Pro, you're going to love that course. But this was basically to serve as an introduction to a tool that you could use to streamline, I say streamline, at first probably not streamline because you're learning, but once you get a hang of things, it can certainly make your life easier compared to having to go through everything by hand and using the handbook to do all that stuff. Ultimately, from the assignments, and you're still wrapping up some of this work, but now you should be able to integrate the design of the individual steel components into a larger steel building design project. So you design tension members, you design compression members, you design the braces as tension only, you design them as tension compression, you design the columns, you design a base plate, you designed some joists and girders, or are currently designing joists and girders. And the goal is to place those individual elements within the context of the framing plans that you were assigned and communicate that information to me on drawings on the final project. Okay? So basically, from the start of the course, you might have been able to draw a shear and bending moment diagram, do some basic structural analysis, maybe describe the properties of steel if you just pull it apart in tension. But now you can put all those things together and basically design something like this, right? So you've got a three-dimensional building. You've got some context now for how the loads act on the structure, some skills to trace those loads through the structure into the specific members that you have to design. And now you can figure out how strong each of those elements needs to be to place them into a, I guess you could call, acceptable design through the structural design process. Throughout the course, we've gone through load calculations. I gave you preliminary framing plans and elevations and said, go through this process, right? So you did the load calculations on assignment 1 and 2, load effects also on assignment 1 and 2, and then member selection was basically all the other assignments. Assignment 3, design tension members. Assignment 4, design a welded connection. Assignment 5, design a column. Assignment 6, design beams and base plates. Throughout the time, I asked you to evaluate the design, and there's a couple things to that. There's calculating the strengths to verify it works, and there's also comparison to design alternatives. In your groups, you had 4 different framing plans. You could consider those design alternatives. And throughout the course, I've been asking you to compare the weights of the braces, how efficient is everything, the total weight of columns, beams, and girders. How does everything compare across the 4 framing plans? And ultimately, the final deliverable is a report telling me why you picked the framing plan you did, what evaluation criteria, weight, space, I don't know, availability of materials, was tension compression better than tension? Lots of things to consider when evaluating the different things that you could possibly do when designing the structure. Ultimately, the deliverable is final design drawings. Maybe you call them design development. They're not really final, of course, because there are a whole bunch of different steel components that you haven't designed yet. You focus on some things like the typical joist, the typical girder, typical column, and some bracing. There's lots of other stuff that we haven't gotten to in the course, but you'll get to in later courses and during your career. So your deliverables are basically a floor plan. And what I'd like to see on the floor plan, I'd like to see the sections for your joists, the sections for your girders. I'd like to see everything labeled, though. I remember last year I got some deliverables that just had like one joist labeled and one girder labeled. I'd like you to label all the joists that the section works for and all the girders that the section works for. I just made it minimalistic here to not overwhelm everybody the first time I showed you a floor plan. But I also want to see some connection details here. I want to see where the columns are, some column lines, some base spacings. And if you have things like steel, it's nice to denote that, you know, the W sections, you want to say, you know, they're to grade whatever, you know, ASTM, A992, grade 50, etc. So whenever you're using structures, you need to communicate this information to the people who are going to build it. They need to know what to buy. And so if you've got HSS or plate steel or wide flange sections, you basically need to tell them the grades. You need to tell them what bolts you're using, what electrodes you're using. And so there's a lot of additional information that you need to outline on the drawings. Think if somebody needs the information to build it, it should go on the drawings on the representative framing plan. Okay? There's some elevations and some bracing. I need to see section sizes for the braces. I need to see design forces for your braces. I need to know where the floors are. And when I say section, usually if you zoom into this, basically what you see is sort of a couple little icons denoting roughly where the joists and girders sit. So this is a girder. Top of steel sits at the top. These are joists framing into the side of the girder. It's just nice to show how everything sits relative to one another in that section. Not crucial, but a nice detail to show for sure. Okay, so we've done a lot of stuff in the class. You still have some work left to do. If you have any questions about the outstanding work, then let me know. Otherwise, does anybody have any questions about anything that we've talked about so far in the course before we get on to other stuff? Okay, so this afternoon, basically I'll be going through last year's exam. So lots of questions about what should the exam look like. There are 2 exams posted currently to D2L. One is from fall 2023. One is from fall 2024. If you look at the 2 and extrapolate, you can probably assume that some things will continue. There's a floor plan. There's an elevation. I give you some information about the building, and I ask you to do a bunch of stuff. And there are 4 questions. They're representative of how much weight we placed on them in terms of discussing those topics throughout the lectures. And so if you're working on those exams and you're wondering, did I get this stuff right? If you work through the exams and you want to know if you got it right, then you can come see me anytime during the week. Usually just send me an email, ask me, hey, can I come see you at this time? Usually in the mornings work better for me because I have to be home a lot of times to be home with my son after school, but I'm happy to go through the exam with you and tell you if you got things right or if you could do things a little bit differently. But I'm going to go through the exam from fall 2024, which was last year. Generally, the averages on the exams are 67% or so. So I think everybody's sitting pretty cozy with a nice whatever grade you have from unlimited attempts at quizzes. The assignments were graded. The average grades on assignments were 70 to 80. The average on the exam is lower. And it's a product of a few things. One, you don't get unlimited attempts to do the exam, and so that's one thing. But the other thing is it's long. I make it long sort of on purpose. I don't want to say the course is easy, but there's a lot of opportunity to get some good grades during the deliverables throughout the term. And so the exam is intentionally a little bit more difficult so that at the end of the day, the average course or the average grade in the class is about a B or a B plus, so that I don't have a class walking out of here with an average of A plus or something like that. Okay, so, but it's a very fair evaluation of all the things that we've talked about. So that's great. I told you a bunch of stuff. Now you can design steel buildings, whatever. What's important is where you kind of go from here, right? This is one class. It's one class in a degree program. Maybe you like structural engineering. Maybe you hate it. Kind of what context should you place this course in, and where do you go from here if you do or you don't like what we talked about during the course? Okay, so there's lots of options, right? They always say, if you could go back in time and change anything, you could do a million different things. There was a little picture that I saw someone post on LinkedIn, and they said there's a million paths that you could possibly have taken from the time you're born to getting here now, but there's also a million paths that you could take from today to get to where you're eventually going to end up. Okay, so there's always lots of options available to you. Maybe you thought, okay, this Taylor guy, he sucks, I hate him, I'm done, like university's over, and I'm going to get out of here, take my C- and say I'm going to go try something else. I did like that he talked about welding though, and so maybe I'm going to go to school to become a welder and make more money than most of my graduate classmates are going to make as a structural engineer. Okay, I say that a bit tongue-in-cheek, but there are so many things outside of engineering that you may have an interest sparked in you over the past 3 years of coursework in school. Engineering is not the be-all and end-all of anything. There's lots of stuff that you can do outside of this, and I encourage you, please, to go try out some of those things if it's going to bring more joy to your life and potentially more money. And so in that case, you're going to go do something else. But I would say most of you, you're probably going to say, well, I'm, 60% of the way through an undergraduate degree, so I might as well just plug on and get on with it. Collect my paper, and then continue and figure something out. And maybe you decide, that's enough of that engineering stuff, I'm going to go do something else anyway. Still go do a welding certificate. A lot of people go into banking because, there's less risk in terms of having stuff that you do kill people, and you tend to make a little bit more money in banking. So there's a lot of stuff that you can go do. You can go write poems if you like too. A lot of people have a very nice life writing poems, and I know a lot of engineers who are actually great poets and novelists as well. In any case, lots of ways to go do something else. You can either get out now or continue and actually have something to save for it and then go do something else at that time. I would say at least half of you are going to take your degree and you're going to say, okay, well, I did all this work. I might as well go do some work in engineering, something relevant. But there are some other things to do as well. You can say, okay, well, I'm going to go work in the field that I'm working in, or maybe I'm just not ready yet. The economy sucks. There's no jobs for me right now. So I'm going to stay in school. You can do a bunch of stuff. You can go do law, go do business, or you can go into grad school and dive deeper into some of the stuff that you learned in engineering. Okay? So the first step is probably, unless you're done, you're going to continue on here and wrap up your undergraduate degree. If you liked what you saw in this course and everything else that you saw before this when it comes to structural engineering, then you should remember this roadmap to doing interesting things in structural engineering at UNB. So you're here currently. Regardless of whether or not you like this class or any of the other ones, you reinforced concrete design, which is a little bit harder than this class, I would say, in terms of the concepts. But for the most part, it's still shear and bending moment diagrams, cross-sectional strength, blah, blah, blah. There are 3 technical electives that are important, and I'm actually going to replace Concrete Design 2 here, because as whether or not that's going to continue to be offered is more of a question mark, but there's a structural timber design or structural wood design class. If you want to be a carpenter after you're done your degree, then you should probably take that class to see kind of what goes into wood design. But there's a class on structural engineering, which is basically CE 2033 on steroids, I guess. CE 2033 already seems like a course on steroids, I think, from time to time. But that's a class where you learn how to write structural analysis programs, use the structural analysis programs to do some design optimization, and learn how to use, I think, a different structural analysis program. So here we used STAAD Pro. In 5043, you're going to write your own software, which is kind of cool. And then you're going to also get some exposure to SAP 2000, which is another structural analysis program used in industry. In structural wood design, you learn how to frame buildings using wood, how to calculate loads on wood buildings, how to select wood members to be strong enough. So it's basically steel design, but you're using wood instead. And then there's structural steel design 2, which is me again. I already told you about what to expect in that class. We talk about structural steel systems, connections, and do a lot more STAAD Pro work in that class. Okay, so if you're interested in structural engineering, those are 3 courses that you should be looking out for, so you can tell potential employers when you're done, I wrote my own software, I can design steel systems, I can design bridges, and I can design mass timber structures, all of which are sort of the avant-garde of the profession at the moment. At the start of the class, and I don't think we have the same 40 people here today. Oh, we're getting close, I guess, compared to previous days, but I asked the question, which best reflects your current position? And there was the answer, I definitely want to be a structural engineer, maybe I want to be, I don't think I want to be, and I definitely don't want to be. And so this is a screenshot of that actual slide from day 1. And so I'll ask the question again, just to kind of see how things have potentially shifted. I was quite surprised, you may recall, at how many were in the B column. I might want to be a structural engineer. And I said my goal was to shift the people from column B into column A, and some people from column B into column D. Okay, so not that I want to force anybody out, but I certainly wanted to make sure that you had some context for what structural engineering was so you can make an informed decision going forward. So like I said, we're not going to get the 40 responses that we got on day 1, but things are sort of shaking out. So the I definitely don't want to be a structural engineer on day 1 was 4, and so it's still 4 today, but that's of the number of people that we have here. I don't think I want to be a structural engineer was 8, and so now there are 7. I definitely want to be was 6, and so now there are 3, and the I might want to be was 22, which I imagine most of them are not here today. But in any case, it's a slight shift, okay, so I'll call that there. We had, I would say, something that was shifted relatively heavily to the left, something that's a little bit shifted more to the right, and I think that kind of makes sense. Not to say that I was trying to encourage anybody to shuffle down to the right at all, but I definitely wanted to provide context for what the profession might look like and what it might mean for you in terms of the kind of work that you're doing. Is anybody here now not in the column B, I might want to be a structural engineer, who has shifted more to the right? Has anybody changed their decision from I might want to be to I definitely don't want to be, or anything less than that? Has anybody shifted from I might want to be to I definitely want to be throughout this course? Has anybody shifted from I definitely want to be to I definitely don't want to be? Okay, so no one wants to share anything. That's fine. I'm not trying to pick on anybody. I'm just curious what particularly sparked a movement one way or the other. So basically what I get from this is everybody who might want to be a structural engineer just didn't show up today for the most part. There are a couple more people who might definitely not want to be a structural engineer. Anyway, for those of you sort of column A, column B, I want to get out and work. Or even if you're not in structural engineering, you want to do environmental engineering or something else, there are some similarities in terms of what the work's going to look like. Okay, so you finish your degree, maybe it's in structural engineering, maybe it's not. What does that look like? Well, for the most part, it's doing engineering design and analysis. So all the stuff that we've done in this course is stuff that you're going to do over and over and over again for 30 years, and then you retire. And sometimes that doesn't sound exciting, but sometimes it can be very exciting, especially when the kinds of projects you're doing the analysis and design for become more and more interesting than stuff that we would have talked here. The major deliverables or outcomes of your work: be preparing construction plans and drawings. So you're currently doing floor plans and elevations, and that's what you're going to help the technicians build. You're not going to be doing the drawing per se, but you do sketches to give to the technicians who will put it into CAD and make it look real nice. But your time is going to be spent preparing construction plans and drawings so that people can build things. And I think that's a very noble outcome. Sometimes you're going to be writing reports or letters. You're going to be telling people that their buildings are in disrepair and they need to be fixed. You're going to be telling people that the code changed, and when they sell that building, they're going to have to reinforce everything to meet building code when they change the occupation of the structure, and that's going to make people really mad. And sometimes you're going to tell people things need to be done when you have competing people who are telling them that things don't need to be done. And so as an engineer, your job is to give an informed and professional opinion about what you think that people should be doing, and sometimes that opinion will be conflicting with opinions of others, and that can get really interesting as well. Those are the major things. Some other stuff you might be involved in doing. Whoever's building the structure at the end of the day, before they even go forward, they're going to say, I don't want to spend a whole bunch of money on engineering. I don't want to send it out for tender if the building I want is not in alignment with the budget I have planned for the building. Someone's got 20 million bucks. They want to build something. An example would be we are supposed to build this thing at the front of the university for $14 million, I think, which already seemed absurd to me. And they ended up spending something like $25 million, and so there's a delta there between what they had planned and what they had to spend to get that done. So the engineer is going to take the first kick at the can, and they're going to say, poorly, in my estimate, and I was pretty bad at it too, that this is going to cost $14 million. And then the client's going to say, okay, we've got $15 million in the budget, and so we'll go ahead with it and plan on having to raise an extra $10 million sometime later down the road. Those of you who like to talk to people will get into business development and develop some client relationships. That's something we never talk about in the program, which is, I mean, it is what it is. It's a hard science degree or an applied science degree. Talking to people is not something we really give you a lot of skill set in, but you have to do work for somebody. At the end of the day, you're an engineer doing work, but the work comes in from people who want to work with you. And so you're going to work for a firm. The firm's job is to make money, and so part of your role might be in sort of schmoozing and dealing with people who you want to come spend their money at your engineering firm. Okay, so that's oftentimes becomes a full-time job for a lot of people who might not care that much about the engineering design and analysis part, but they can tell you all about it and tell you why the firm is the best place to get that stuff done. You're always going to have to be doing learning forever, and so it might say, I wrote my last exam, I never have to learn anything ever again. Well, unfortunately, everything changes all the time. New softwares come out, new codes come out, new methods and research are done to say things should be done differently, and so you're always going to be learning, not as intensively as you are here, but there's ongoing lifelong learning that you're going to have to be doing. Project management might be something that a lot of you get involved in. It's somewhat similar, I would say, to business development. It's basically dealing with people to make sure things get done. And so engineers, you don't learn very much to deal with people in the program. You might have some innate skill set to deal with people, but they also call project management herding cats. It's getting the cats where they need to be when they need to be there. And so a lot of it is making sure that things go smoothly. If problems come up, you can deal with them. If things aren't getting done, you know who to talk to get them done, and you keep the project moving forward. You can only imagine, just think of the typical person who gets through the engineering program, don't like to talk to anybody, but they can do all this stuff really well, and all of a sudden they're with 5 other people who have a similar skill set, and they're trying to get something done. It's not going to get done unless you have somebody who knows how to talk to and deal with people to make sure that the things get done when they need to do it, and that those things get done on time and under budget, or only slightly over. The other thing that I would say no engineering firms do well at all, there might be one diamond in the rough who does some of it, but it's talent management. So project management is dealing with the people on the projects to make sure things get done, but the talent management is to make sure that the people who are actually doing these things want to keep doing it and can do it to the best of their ability. You're going to have, or have already had, a boss or a supervisor before. I can say 50% of the time you're going to hate them and 50% of the time you're going to love them. Rarely are you indifferent to them. One day you might be one of those people. And so you're going to have to know that some people are not going to like you. Some people are really going to like you. No one's really going to be indifferent. But as somebody responsible for the talent at engineering firms who are responsible for doing these things, you need to make sure that they get ongoing professional development opportunities, that they get opportunities to do more interesting projects, that you're giving them feedback as to how to improve going forward, and you're directly responsible for their career path. Okay, so that's not something we talk about in this program, how to coach somebody through their engineering career, and that's something more or less that you're going to see someone do really well for you, and if you're a smart person, you're going to emulate those things for other people. Where are you going to be doing these things? Well, in the first lecture, I outlined some of the key players in building construction. So the owners have engineering departments, there are engineering consultants who do the work, there are general contractors who actually build the stuff, and there are opportunities for you with any of these entities. Okay, so maybe you're working for the engineering department of the owner, maybe you're working for the firm doing the design, maybe you're working for the general contractor doing the construction and handling the sub-trades. Generally, you can lump a bunch of different companies into these sort of, I would say, sectors. You've got your private sector consultants. So you want to work for a great big consulting firm, you can go work there and do engineering design until you die. If you want to build stuff that helps public infrastructure, you can work for the province, municipal governments, public utilities like NB Power, and you can make sure that people get power for their homes during winter, and you can do that for 30 years until you retire. Maybe you work for private utilities like Liberty Utilities, they're a gas line, maybe you're working in telecommunications. At the end of the day, these companies need to keep the infrastructure working so that people can do things like heat their homes, communicate with people, and so there's lots of infrastructure there that needs to be managed, and you can go work for any of those companies. There are private firms, or not firms, but I guess you could say companies that make stuff. I would say 80% of you at some point will either work for or work with Irving. I don't know if you know how much of a foothold I would say Irving as a group of family companies has over the province, but if you go to St. John and you drive anywhere, pretty much it's owned by Irving. And so there's the oil, and there's the, Irving Energy, which has oil and natural gas. There's Irving Forest Products, which has the paper mills, the tissue mills, the pulp mills. There's Irving Construction, which has Ocean Steel and Stresscon and FCC, and what's the other one? There's another construction, Gulf Operators. So just because it doesn't say Irving doesn't mean they're not. There are a whole bunch of companies that you could potentially work for doing engineering things in any of those instances. There are the big construction firms, and so Bird Construction's currently wrapping up or managing the construction of the Justice Building. Ellis Don built this great big overpriced structure at the front of our school, and they're also building the Performing Arts Center down at the corner of King and Regent Street. If you just want to talk about how cool structural steel is, you could potentially work one day for the Canadian Institute of Steel Construction. A lot of stuff going on there. What does CISC do? Well, they publish the handbook, and so they update that so that we've got new design tools to use so you can learn about structural steel. They advocate for the structural steel industry, make sure that Canadian steel makers can sell their products for a fair price in a fair market, and they develop a lot of educational material as well for professional development opportunities if you want to take advanced learning courses, and you can go check out some of those and see if that's something you might be interested in after you finish the degree and start working somewhere. Why would you go work now? Well, you can get a PN, right? The big thing and the big goal is to get your license. Once you graduate, it's 3 to 4 years, depending on whether or not you've got some pre-graduate experience. It's the quickest way to make some real money, which is great. I have $3 signs to denote that that's a reasonable amount, but not a lucrative amount of money. You can get some real experience doing some real things right away, and so you can make an impact on the community around you as soon as you start working. If you want to turn $3 signs into 4 or 5, the two things that are important to you should be to learn what the business is about, how does the business operate, what is the business value, and understanding the client requirements. How do you get the client to figure out that they want you to do the work for them so that they go to your firm and not somebody else's. Okay, so these are the routes to, I would say, 4 or even $5 signs if you can do those things. And if you want, you can always come back and do more school another day. You can do a Master's of Engineering or an MBA or do some kind of research-based degree. The one thing I would say is always, 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 despite your risk profile, take the company matched stock options if you do work for a private firm. And I only say that because when I worked at Stantec, I took it because basically you put some money and they put some money and it gives you equity in their company. That stock sits on, I think, the TSX, which is the Toronto Stock Exchange. When I started working there, it was worth $27. When I finished working there, it was $67. And I sold it all, and now it's worth $140. Okay, so a lot of times the engineering firms give you some ability to take some equity in the company. Almost always the equity of that company is going to go up. Don't take that as financial advice, but at the very least, the company is going to give you some money. So at the very least, it's a 50% return for every dollar that you put in. In terms of licensure, that's the first thing you need to work towards, and ultimately the firm is paying you to offer a professional opinion, and the way that you state that your opinion is professional and in line with the standards of practice is by stamping the drawings. And so you're working on developing drawings right now. If you were at an engineering firm, ultimately you'd draw them, make everything work, and then you'd put your seal of approval to say all this stuff was done in accordance with codes and standards. It's not a guarantee, and so it does not guarantee that the building's not going to fail. It's just that you think it won't in accordance with your own best practice. So what that means is you're taking professional liability and accountability for that work, which basically means if something bad happens with the structure, you say you're designing your building now and you build it and the roof caves in. The first thing they're going to do is say, whose name is in that circle stamp down there, because they're going to start coming for you for some money, right? And that's either going to come from professional liability insurance or liability insurance through the company. If you're working for a big firm, usually the lawsuit goes to the company. If you're working on your own as a sole proprietor, they can come after your house and home. So work for a company, or at least incorporate if you're going to work on your own, and make sure that you're comfortable sealing things before you actually put your stamp on them. It's a minimum standard. That care in the field of competence was taken in developing the drawings. And you can only call yourself an engineer or use the suffix PEng if you have a license in the province. Okay. So in Canada currently, anyway, every province currently has its own licensing board. I was licensed in New Brunswick. I used to be licensed in Ontario when I was working professionally, and also in Nova Scotia. I have to keep my license in New Brunswick because when I teach these courses, I have to be licensed for the course and program to be accredited. But every province has its own association and own licensing, so you can only stamp drawings in the province of construction if you're licensed as an engineer in that province. Question, Laura?
Did you get licensed in Ontario versus Nova Scotia? And then what was the process like switching between the provinces?
So normally you don't switch. The first thing you do is you have to get licensed in your home province. And then once you're licensed in your home province, normally it's a quick transfer, not a transfer even, but an equivalence of licensure. And so basically you're going to say, I have a PEng in New Brunswick. My degree is from here and everything's good. And you're just going to send them an application form and some money. And they're going to say, okay, we'll review it, get back to you anytime between tomorrow and a year. And then they'll send you a note with a little stamp in the paper that say, yes, you're licensed to practice in Ontario. But you have to pay that license fee every year. It's normally $400 per license per province, so it can add up quickly. Same thing elsewhere. So Nova Scotia, to say, hey, license in your province in New Brunswick, but I want to do some work in Nova Scotia, send them a paper and some money, and they'll give you a license there too. But the first big milestone is to get licensed in the home province. Currently, they're trying to negotiate between the provincial, interprovincial free trade agreements. They're trying to get licenses in a province immediately applicable to other provinces as well, which is a change that may come soon. You may be able to work in Nova Scotia as an engineer licensed in New Brunswick and apply a stamp from New Brunswick to a project in Nova Scotia coming up maybe in the next 5 years even. Okay, so that's something to look out for. So those are some things to consider if you want to work. There's some places to go, some things you're going to do, and some routes to try and make some more money a little more quickly. Does anyone have any other questions about what that might look like? Yep.
After you work your 4 years towards your PNs, what's that PN's exam like? Like the structure of it or like the content?
It's in Canada, it's quite simple. It's basically about law and ethics. The exam is not technical. You don't have to draw shear and bending moment diagrams or calculate strengths of beams. You basically write what's called the National Professional Practice Exam. You have to know what the APEG-NB Code of Ethics is. You have to know some law about mostly Canadian common law, and it's different if you're in Quebec because there's statute law, which is different because we've got the British system, they've got the French system in terms of application of law in the province. But it's a multiple choice exam, and you'll take law and ethics in your last year. And basically, as soon as you take law and ethics and graduate, you should go write that so you don't forget all the stuff. I wrote it 5 years or 6 years later, and I forgot all the stuff, so I had to read the book and do all the stuff again. But it's just a professional practice exam. It's 2 hours long, not very difficult.
So you can write it right out once you get out of school?
As soon as you graduate, you should be able to write that. You have to get yourself enrolled as an engineer in training.
Yeah.
And so give somebody an application and some money, right, always. And they'll let you be an EIT, and once you're an EIT, you should be able to go write the practice exam. Sometimes in some provinces, they may want to make sure you have like 3 years of experience before you do that. Some don't have that requirement, but that's something that you can check on before you try to register for the exam.
Yeah, I thought maybe you'd have to get your hours before you wrote it. I didn't know.
I think it's provincial dependent for the most part. Yeah. The other thing is if you want to do work in the States, and I should change this, if you want to work in the States, then there are technical exams. There's what's called Fundamentals of Engineering exam. It's a 6-hour exam that's technical. Calculate the strength of beams, calculate the soil compressive resistance, do a bunch of stuff, and it's all within the American standards, and so you have to learn a little bit about the American standards, but if you want to do any work down there, you have to write the FE exam, and the best time to do that, again, is right after you do this. And again, to write that, you apply and send someone some money, and then you go write it, and hopefully you pass. And once you have that and you work for 4 years, there's also a professional engineering exam, which is an 8-hour exam, also technical. And so they've got a little bit more of a rigorous approach to licensure in the States. The reason we don't is because we assume that the Canadian Engineering Accreditation Board, which you probably see from time to time, graduate attribute indicator, graduate attributes, accreditation, blah, blah, blah. Basically, the process that we have to follow to make our program accredited in accordance with that accreditation board absolves the responsibility of anybody to give you another technical examination. They assume you have the technical skill set and competence, and that should be demonstrated through appropriate experience on the job before you get a license. Okay. So we always like to talk about grad school. I'm a professor, and one of the things that I need to do as part of my job is supervise graduate students to do research in the field of structural and earthquake engineering. What is grad school? Basically, you continue to take some more courses. To do a master's, you have to take 5, and they're usually a bit more involved than undergraduate courses, and you take them over the course of 2 terms. You can work as a TA and make a little bit of money. You get to perform research with some professors doing something I hope is interesting for a little bit more money. So you get paid to go to school, which is kind of cool. Right now, you're just shelling out money to come get a degree. At least if you're doing a master's, normally master's students get paid like $25,000 a year, so that offsets your tuition and gives you a little bit of money for food and to live somewhere. A little bit, right? Not a lot. But it's better than into more debt based on paying tuition only. You write a great big long report about the cool stuff you do, you present it and answer questions about it before a committee, and ultimately, as professors, we need to take that work that you do and put them into papers for other researchers to read, and so you can write some papers and present your work at some interesting national or international conferences. When I was a PhD student, I got to travel to Chile, I got to travel to China to go present some research, and so there are very few opportunities for you to travel on someone else's dime to those kinds of locations, and so that's something that can be fun. Sometimes engineers with graduate degrees earn more money. I posted the engineer salary report from 2024. There's a firm that for PEI, Nova Scotia, New Brunswick, and Newfoundland and Labrador, they do a salary survey, present average salaries, median salaries, top 25%. And if you look at the salary survey, those with graduate degrees statistically make more on average. But there's also a better route to advancing in the company. You get to do more interesting projects. Maybe you work on higher profile things. And so that's a way to increase your salary relatively quickly, as well as to start with a graduate degree. You usually get a year. If you do a master's degree, you have to get 4 years to get a license. And if you do a master's degree, they'll waive a year. So when you're done your master's, you have another 3 years to do. If you have pre-graduate experience from co-op or summer terms from your undergrad, if you have that and you do a master's, then you only need 2 more years before you get your degree. It's becoming a standard for professional practice, especially in the States, for licensure in structural engineering anyway. And Dr. Arjamandi just told me he read something recently that the prevalence of AI and the ability of AI to do a lot of things that fresh grads can do has diminished the long-term value of an undergraduate degree by as much as 50%, making a master's and potentially, for rare cases, a PhD something worth going for if you want to have a fun, interesting, and rewarding career. Okay, so you get paid a little bit of money and you get some experience for doing it, so the opportunity cost is quite offset, and you can always go do some engineering stuff later. Okay, so there's some options there, and for those of you who are sort of the ones, what would I say, over here, going to go do something else, you didn't find what you were looking for. If you're looking for something else, I always say this because sometimes you're just in engineering because someone told you had to be there, right? A lot of times a friend said, well, you're not going to get anywhere without engineering. A parent might say you're going to be a lawyer, an engineer, or a doctor, and so you had to pick one of those 3. But the most important thing is that you do something not that you have to do or that people tell you to do. What I would say is you're not trying to fill a world's need, and so what you should be doing is ask yourself what makes you come alive and go do that thing. Because the world doesn't need engineers and lawyers or bankers or poets that are disinterested. They need people, the world needs people who have come alive. And so whatever makes your heart beat and your skin sort of get those goosebumps, you should go do those things, because you're never going to have a better life if you're doing something just because someone else told you should do it. There's a Japanese concept of ikigai, which you may have heard before. It's the Venn diagram, and it's the intersect of doing the things that you love, the things the world need, the things that you're good at, and the things that you can get paid for. So hopefully you can find that center so that you can have a rewarding life. This is basically the Japanese equivalent of do what you love and you'll never work a day in your life, right? So it's basically that's the English equivalent or the English proverb associated with a similar concept, okay? In any case, I hope that you enjoyed the course. We've got the exam on Saturday and a review period this afternoon. Please keep in touch, though, regardless of whatever you do. I'm active on LinkedIn, and you can connect with me there. I look forward to following your careers. And I'll see you all this afternoon for the exam review.